Hello everyone, this is my review for Kepler's laws of orbital motion. So for this, I'm going to go over each of Kepler's law and then show you how to see whether or not a planet or any orbiting object follows all Kepler's law. So Kepler's first law states that a planet orbits around the sun or any object orbits around the sun in the shape of an ellipsis where the sun is at one focal point. So you can see down here, this is an ellipse. So the sun is at this side, here's the planet, and then this other focal point, it's just a math review for ellipses. It is just like the two center points of an ellipse. This focal point is empty in real life, but the sun is always on one side. So the way we can tell how flat an ellipsis is through the eccentricity. So the eccentricity is a measure of how flat an ellipse is. If we have an eccentricity of 0, we get a perfect circle. And you can see if we keep on going up, it goes between 0 to 1. 0.5 is kind of more oval. 0.8 is a lot more flat oval shape. And if you see here, the most eccentric at 1.0 is a flat line. So a way that we can calculate eccentricity is just to calculate d over L, where d is the distance between two focal points. So we see this right here. And L is the distance between this entire horizontal length. And you just divide them. So to provide an example, let's say we have an ellipse. Got two focal points here. Let's say D equals 4 centimeters. Then L, the entire length, is 10. We can just calculate eccentricity by doing D divided by L, which is 4 divided by 10, which is 0.4. You can see 0.4 is kind of close to halfway, so that's why we have an oval shape. Remember, if it's circle, it's a perfect circle. If it's 0, it's a perfect circle, but the higher number, so closer to 1, it's a more oval shape. So Kepler's first law just states that planets are in the shape of an ellipse, not a perfect circle, and by calculating eccentricity, you can be able to see that. So this one's the easiest one to remember. Kepler's second law is a little bit more confusing. Kepler's second law states that the line connecting the planet and the sun sweeps across equal areas in equal amounts of time. So what that basically means is the closer the planet is to the sun, the faster it moves. So you can see right here at this point, at the same time, the planet moved from this here to here. It moved a lot faster. When it's this far away, at the same amount of time, let's say a year, it only moved this far away. And when it's the farthest point from the sun, it only moves this small distance. So the closer it is to the sun, the faster the planet moves. We usually call the closest point the perihelion. So you can see right here's the sun, the perihelion is to one to the right, and the aphelion is the farthest point, which is usually the opposite end of the ellipse, and it's it is the point at which the planet moves the slowest. The reason why that the planet moves so much slower is because if you remember gravity, the closer two objects are to each other, the stronger the force of gravity. So the stronger they'll be pushed or pulled. So at the perihelion, gravity pulls the gravity of the sun pulls the planet more, so it moves faster compared to here where it moves slower. So let's say I gave you different speeds at these different points. The one at the perihelion is supposed to be the fastest, and the one at the aphelion is supposed to be the slowest. That's how you know if it follows Kepler's second law. The closer it is to the sun, the faster it moves. The farther away it is from the sun, the slower it moves. Finally, there's Kepler's third law, which states that the square of the period of a planet is proportional to the semi-axis length, r cubed. and they're equal in AU. So that basically gives this equation. The period squared, so T squared is equal to the semi-major axis length, R cubed. So let me draw an orbit. That's a bad orbit, but we'll just go with it. The period is just how long it takes for the planet to move one complete orbit. And the semi-major axis is just how far it is from the sun. So this is R. Or not how far it is from the sun. It's more about, sorry, that's a little bad explanation. It's between this point. It's how far it is to the center of the ellipse. So you can calculate this. So let's show Kepler's third law. Let me zoom in. We did this table previously. So let's look at Mercury. We had a planet, its period is 0.24, semi-major axis length is 0.39. I remember we did this table, so we had t to the power 2, 0.24 to the power 2. So we did this. We got a 0.0576. Then we took the r, 0.39, and took it to the power of 3. We got 0.0593. You can see that these numbers are very close to each other. And we actually divide them. So let's do t squared divided by r cubed. So this number divided by this, you get 0.971, which is basically close to 1. So we took the t squared, so 0.24 to the power 2, we got this number. R cubed, 0.39 to the power 3, we got this number. They're so close together. When you take their quotient, their division, you saw that they're very close to 1 when you round. So that's what Kepler's third law states, that these two numbers, the t squared and r cubed, are basically equal. When we did this with other planets, you can see the same thing. So let's look at Venus. Venus 0.61 for t, 0.72 for r. T squared, we got this number. R cubed, we got this number. 0.3721, 0.3732. They're again very close. So again, the t squared, r squared are basically equal. They're close to 1. And that pattern falls for any other planet of the solar system. And that's how we got this equation. But let's do a practice problem, because now you can use that equation to solve for the missing period or r. So we have the Mercury's distance to the sun is 0.39 AU, and we have to calculate its orbit. So let's do another thing here. We're doing, let's do this red. T squared equals r cubed. And that first problem, I'm just with 3. R equals 0.39 AU. And we're looking for T. So this is what you do. You basically just plug into the equation. We have T squared equals 0.39 to the power 3. Let's calculate that. And that's going to be, if you use a calculator, 0.0593. So how do you find T? This is not the answer. You have a squared here and take out the square. Let's write this again. T squared equals 0.0593. So what you have to do to get rid of this squared is just straight take the square root on both sides. So you take the square root of t squared and take the square root of this. So square root of t squared is t. And you take the square root of this, and you should get 0.24. And if you look at the table, that's the right number. Let me show that table again. Because we did, this is based on Mercury. T is 0.24, 0.39, we got the right answer. Okay, but now let's do another problem. Let's say with a new planet, and it's 0.62 AU from the sun, calculate the period. This is very similar. So for number 4, R is 62, T, we don't know. So we do the same thing. T squared equals 62 to the power of 3. T squared equals 238,328. We do the same thing. Let's write it again. We just take the square root of both sides. And you see that t, if you do the calculator, will be about 488 years. 488 years. So let's do something a little bit different. Let's say we do a similar problem, but now we have t equals 62 and r we don't know. So this time instead we're going to do 62 squared equals r cubed. So if we do 62 squared, we will get 3,844 equals r cubed. So this one you can't take square root. You have to take what's called the cube root. So this should be an option on a calculator where you do the square root sign, but you put a little 3 right here. So instead of taking the square root, you're taking the cube root because r is cubed. If you do that, your answer should be 15.67 equals r. And this is in AU. Now in the calculator, usually how it looks like, you might have to press shift. You see usually this symbol. Sometimes you see this symbol with an X on it. So that's how it usually looks like if you look for your calculator. Another way you can do it is sometimes you see x to the y. That means an exponent. You can put the exponent as 1 divided by 3, and that'll be the same thing as cube root. But I would suggest just try to look for cube root first. All right. Let's have a review of Kepler's law. Just remember for each of the laws, let's review them very quick. First law, planet orbits around the sun in the shape of an ellipse. So we usually find eccentricity. If we find eccentricity is like bigger than 0, we can tell it's not a perfect circle. Second law, they sweep across equal areas and equal amounts of times. These areas are equal, but they move at different distances because as the planet is closer to the sun, the faster it moves. Finally, third law, it's the equation where t squared equals r cubed. If the period squared is equal to the semi-major axis length cube, then that follows Kepler's third law. Okay, that's all for this review, and then hope you can, if you're planning to retake Kepler's law quiz, make sure you also do the assignment because you can't do the quiz unless you complete the assignment. All right, thank you.